Welcome back, everybody. So, chapter 3 is all about probability. Chapter 1 was like introductory stuff. Chapter 2 was all about descriptive statistics, right? How do we describe everything that's going on? And chapter 3 kind of does a little sidestep and says, okay, let's talk about probability now. Now that we've gotten our feet wet a little bit, let's talk about some probability. And I think I really enjoy probability. I think it's interesting. So this is kind of like one of my favorite chapters. It's a bummer that we get through it so quick. Okay, so let's talk about basics. Today, section 3.1 is just like building blocks. Like, okay, let's set some ground rules. Okay, so when I talk about a probability experiment, that can be any action or trial through which specific results, counts, measurements, or responses are obtained. Okay. Taking a probability experiment is an action, and we call those actions trials, whether that be flipping a coin, whether that be rolling a die, whether that be pulling a card. The action is the trial through which specific results, and that could be counts. How many times do I see this thing happening? Is it a head? Is it a tail? Measurements, responses. I'm going to randomly choose different parts of the day to record the temperature. Those would be measurements. I'm going to randomly choose students and pull their test scores. And then I'm going to say, okay, what's the probability that I get a kid with an A? The probability experiment is the action, which is the trials, through which specific results, counts, measurements, or responses are obtained. Okay, the outcome. The result of a single trial in a probability experiment. When I talk about the outcome, that is the result of a single trial in a probability experiment. So I flip a coin, I get heads. The event, or sorry, I shouldn't say the word event yet, we haven't defined it. The action is me flipping the coin. I do a first trial, I flip the coin once, it comes out heads, the outcome is the heads. The result of a single trial in the probability experiment. A sample space. Sample space is the set of all possible outcomes of a probability experiment. The set of all possible outcomes of a probability experiment. So if I flip a coin, my sample space is heads, tails, right? That's the only possible things that could happen. And yes, I'm excluding the time that if I flip a coin and it landed on the side. I'm going to say that that's never going to happen. In pulling a card out of a standard 52 card deck, I mean, the sample space could depend on what I'm looking at. Are you looking for clubs? I guess no. The sample space would not change. Sorry, I lied. The sample space would not change. The sample space would be all 52 cards, right? That would be the sample space. The what happens in result of that, the outcomes would be different. An event consists of one or more outcomes and is a subset of the sample space. An event consists of one or more outcomes and is a subset of the sample space. That's what I'm talking about when I say, okay, what if I pull a club? The event is me pulling the club. It is a subset of the sample space, which means that, okay, if I say pull a club, the event would be, okay, ace of clubs, king of clubs, queen of clubs, jack of clubs, 10 of clubs, and so forth, all the way down to 2, right? If I say rolling an even number, okay, the event is 2, 4, or 6, right? It is a subset of the entire sample space, 1, 2, 3, 4, 5, 6. Okay, so suppose we want to run an experiment with rolling a single die. Oh, I kind of just said it. Ooh, yikes, sorry. What lists all possible outcomes, right? And these two things are basically like the same thing. Listing all the possible outcomes and defining the sample space is really the exact same thing. We just write it differently. Like sample space, we write basically as a set, right? Like roster notation. Okay, I could get a 1, a 2, a 3, a 4, a 5, or a 6. You don't have to be so picky when I say list all the possible outcomes. We just say, okay, 1 through 6. Right? Rolling a 1 through 6. When I say list out, what is the sample space? Okay, list it out in roster notation. List a few events. Okay, so a few events would be rolling a 1. Oh, sorry, no. Comma needed. Rolling a 1. Right? That would be an event. Rolling a number greater than 3. Okay. Give me an event. Somebody give me an event. Carter.
Even number.
Rolling an even number. So my 2, 4, or 6. Right? Rolling a number divisible by 3. 6 and 3. So this is how we would define events. Okay. Suppose we run another experiment, but now we flip a coin and roll a die. 2 events that would be what we are going to call independent events, ones that do not have an effect on the other. Right? There's going to be a big difference between independent and dependent events. But independence means basically that one event is not going to affect the other event's probability. List all the possible outcomes and list the sample space. And I'm really going to do this on one text box here. It is. Okay, I'm just going to delete that. Because those are the same things. When I say, what is the sample space? That is listing out all the possible outcomes. Okay, now think about it. If I flip a coin and it comes up heads, what are the possible outcomes for me rolling a die? 1, 2, 3, 4, 5, and 6, right? I could have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, right? The other option, instead of rolling a heads, is a tails. And I have 6 options based off of me rolling a tails. Tails 1, rolling a tails. Tails 2, 3, 4, 5, 6. It's got my screen shade there. How many total things are in my sample space? 12, right? I've got 12 things happening. Okay, name an event. Give me an event. Head 6.
Heads 5 and 6.
Heads 5 or 6. Now, be careful the way you word things. In probability, the words and or carry a lot of weight. Could heads 5 and head 6 exist? No. So that sample space would look like that. You know what I mean? Something not occurring, which also means this, right? The null set. So, but if I change my wording to say, instead of heads 5 and 6, if I say heads 5 or 6, then I say, okay, that's heads 5, heads 6. There are 2 possible successful events. 2 possible successful outcomes in that. The book does a tree diagram for this, and I thought that was really helpful in seeing this, especially when it branches off like that. You know, this gets down to the problems which I believe we'll talk about soon. Yep, in 2 slides. The ones where I say, okay, I've got 3. I'm sitting down for a meal. I've got 3 different appetizer choices. I've got 5 different entree choices and 2 different dessert choices. How many different types of meals could I have? Right? Those kinds of things branch off like that. All right. Another definition that we have is called a simple event. a simple event. A simple event is an event with a single outcome. A single outcome, a single success. Heads 3 is a simple event. Heads 3. Heads even is not simple. An event that consists of more than one outcome is not a simple event. Heads even, not simple. Heads 5 or 6, not simple. Heads or tails 2, not simple. Okay. Tails 5, simple. Tails number less than 2, simple. Tails number less than 2, right? So you got to be careful of, okay, actually think about, well, how many different events, how many different outcomes could I actually have in that case? Well, there's only one number less than 2. So tails number less than 2, there's only one there. All right. So let's talk about what's called the fundamental counting principle. That's that meal options thing I just talked about. If one event can occur in m ways, and a second event can occur in n ways, the number of ways those two events can occur in sequence is m times n. Let me state that again. That is the fundamental counting principle. If one event can occur m ways, and a separate event, independent event, can occur n ways, then those two events in sequence of one another can occur in m times n ways. And that can be extended for any number of events occurring in sequence. So I just got done saying, I forget the numbers I used, but I think I said, okay, 3 appetizers. I've got 3 appetizers to choose from, right? I've got 5 different entrees to choose from. I have 2 different desserts to choose from. Well, then I know I could say, well, if I've got 3 appetizers, 5 entrees, 2 desserts, 3 times 5 times 2 is 30. There's 30 different ways I could choose a meal. That's called the fundamental counting principle. Don't believe it? Make a tree diagram. I've got appetizer 1, appetizer 2, appetizer 3. Out of each one of those appetizers, I have 5 different branches coming off of those because I have 5 different options. After choosing appetizer 1, I've got entree 1, 2, 3, 4, 5. After choosing appetizer 1, entree 1, I've got 2 different desserts to choose from there. And if you count up all the leaves, if you count up all the branches, then you know you got 30 different possibilities. For example, another one here. You're purchasing a new car. The possible manufacturers, car sizes, and colors are listed in the table. How many different ways can you select one manufacturer? I just use the same numbers. Oh, no, good. How many different ways can you select one manufacturer, one car size, and one color? Use a tree diagram to check your result. So I've got 3 manufacturers, I've got 2 sizes, and I've got 4 colors. How many different car options do I have? How many? 24. I've got 3, 2, and 4. 24 different options to choose from. So if I wanted to make a tree diagram to demonstrate that, okay, I've got Ford, GM, and Honda. That's my first decision. What manufacturer do you want to go with? Well, and then based off that, I have 2 different sizes, a compact or a midsize, for each one of them. And once I choose compact or midsize, I then have 4 different choices to choose from at that point. So 1, 2, 3, 4. I have white, red, blue, black, or green. And that process can be repeated for every one of these, right? So it's 4 plus 4 is 8, plus another 8 is 16, plus another 8 is 24. 24 different options to choose from. That's called the fundamental counting principle. Another example we have here is a very classic example. The access code for a car's security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible when each digit can be used only once and not repeated? Each digit can only be used once and not repeated. How many digits can I choose from in my first position? 10. I have 10 digits to choose from. 0 through 9. Okay. How many digits are there to choose from in my second spot?
9.
I've chosen one already and I cannot repeat, so therefore I have 9. How many digits do I have to choose from now? Because I have chosen one already, I've chosen a different one now, and now it's going to be 8. I have 8 options to choose from. And now I've chosen 3 of them, so my fourth digit has to be what? 7 choices to choose from. Okay, this is the fundamental counting principle, right? This is the fundamental counting principle. I've got 10 options in my first digit. I've got 9 options in my second digit, 8, and then 7. So what do I do to find how many different ways I could have it? Just multiply all of those together. 10 times 9 times 8 times 7. 56 times 90. Don't know that offhand. 56 times 4. No, I'm not going to do that. It's a big number. 10 times 9 times 8 times 7. 5,040. 5,040. Okay. So what if I put some more stipulations in there? What if I say, okay, each digit could be repeated? How does that change things? 10, 10, 10, 10, right?
10,000.
I have 10 options here all the way through. 10 to the 4th, right? Or in other words, 1 with 4 zeros after it, 10,000. 10,000 different options. So you guessing the correct code right off the bat is you have a 1 in 10,000 shot at that. Each digit can be repeated, but the first digit cannot be 0 or 1.
8,000.
So I've got now, are there any stipulations on the second, third, or fourth digit? No. So those can stay 10. What's my stipulation on my first digit?
8.
Right, it can't be 0 or 1, so I have 8 options.
Still making more sense.
So 8 times 10 times 10 times 10 is 8,000 options. And you can see I could put a wide variety of stipulations in there. Okay, I only want even numbers. It can't be repeated. Or I only want odd numbers. Or I only want ones divisible by 3. And then you just have to figure out, okay, how many different options that I could have. But because those are independent, then I can just multiply them together. They're happening in sequence from one another. All right, so let's talk about types of probability. Shifting gears a little bit. Let's talk about types of probability. The first type of probability that we have is called classical or theoretical probability. Classical or theoretical. I kind of bounce between using the words classical and theoretical. I forget which one the book uses. They tend to, I think, use more of the term classical probability. I learned it as theoretical. But classical probability or theoretical probability is used when each outcome in a sample space is equally likely to occur. The classical probability for an event E is the probability of E, and that's the notation there, P of E, is equal to the number of outcomes in the event, the number of successes, basically. That's how I like to define it. Successes over total. And you have to get out of your head success being something good, right? Think about successful trials as things that you are saying is going to happen. So a classical or theoretical probability is basically our classic, I like to think of it as our classic examples, like rolling a die, like flipping a coin, like pulling a card, right? The what if statements. Right? What if I, randomly drew a card out of a deck and I wanted it to be a club or a heart? That is what's called classical probability, theoretical probability. The number of outcomes in the same, I would say, okay, I'm going to find all of the total successes, count how many cards would be a successful trial, and then divide it by the total number in the sample space, so 52. So let's take a rolling the die example. You roll a 6-sided die, find the probability of each event. Okay, rolling a 3. Rolling a 3. How many successes? There's only 1 3 on a die, right? Out of total? 1/6, right? Rolling a 7. Right. Because there are no 7s on a die. Things get tricky when we add in a second die. Rolling a number less than 5. How many successful outcomes? 4 of them, right? 4, 3, 2, or 1. So 4 out of 6. So you have a 2/3 probability of rolling a number less than 5. Which means out of every 3 rolls, you should expect to see 2 come out less than 5. Okay. Now, the difference, but the opposite of classical theoretical probability is what's called empirical or statistical probability. This is, okay, you have ran an experiment. You have ran an experiment. You have done something. You are going to look back at what you did and calculate the percentages of things happening. That is empirical or statistical probability. Based on observations obtained from the probability experiments, you've done something. You've completed some sort of experiment. You're looking back at your results and saying, based on this, I have a 60% chance of. Basically, like, it's funny, you guys come in and roll the die from time to time. There's a difference between theoretical or statistical probability. Theoretically, if you roll the die, if you roll it 6 times, you're eventually going to get that number that you want to come up. Or statistics say, theoretical probability says that if you roll it 6 times, you should expect to see one of those numbers come up. However, if you roll it 6 times, is it guaranteed to get that number to come up? No. You could take an experiment, roll that die 6 times, and then you got no 1s coming up, or no 2s coming up, whatever it may be. Your empirical probability, your statistical probability, was that you had 0% happening. Your empirical probability was 0 out of 6 trials. So therefore, your probability was 0. You have to think about statistical probability different from statistical probability different from theoretical probability, based on observation. The empirical probability of an event E is the relative frequency divided by the total, or basically, the relative frequency of that event, which is frequency divided by total, F divided by N. Okay. So, for example, here, a company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart shows the results. what is the probability that the next adult surveyed read only print books during the next year? So I have done my study, right? I have done an experiment. I have gathered data. I have gotten percentages. What is the probability that the next person I choose is going to read only print books? Okay, what's the frequency of read-only print? 578. What's N? What was it? You already added up? 1490? Oh, duh. Yeah. 1,490, right? So my relative frequency here is 578 divided by 1490, and I get 0.388. 0.388. So what's my percent? Around that, right? Yeah. What's my percent probability that the next person I choose will read only print books? 38.8%. So I can, with relative confidence, say that the next person I choose is going to have a little less than 40% chance that they are going to read only print books, based on these results, right? And that is statistical probability. You've gathered statistics, empirical probability. You've gathered statistics and said, okay, based on these results, I can now say this percent about the future. Okay, and that is different from theoretical probability. Theoretical probability, I would take a look at something a little bit more, it's hard to actually calculate a theoretical probability in this way, right? Got to look at something that would be a little bit more independent. All right. Now, this is different. This ties in with empirical and statistical. There's one more type of probability. Don't think of this going together. The law of large numbers. I know that's a really weird name. But basically it just says that the more trials I run, the more experiments I run, as experiments are repeated over and over and over, empirical probability approaches theoretical probability. They will go together in the infinite. Okay. As I increase my amount of trials, as I increase the amount of times these things are going to happen, the probability, the empirical probability, will generally approach my theoretical probability. Will it ever be the same? I don't know. But that's not what we're saying here. It's going to approach that value. So what does that mean in terms of my rolling the die? The probability of rolling a 1 is 1/6, right? Well, if I roll my die 6 times, I expect to see 1 once, right? But that might not happen. What if I increase my trials from 6 to 6 million? To 6 million. I would expect to see, as I increase my amount of trials, I would expect to see my number of ones get pretty close to 1 million, right? That's the law of large numbers. As I increase the amount of trials, the bigger I increase my amount of trials, the closer empirical probability looks like theoretical probability. The closer statistical probability represents classical probability. Okay, so sidestepping from that, then there is this thing called subjective probability. Results from intuition or educated guesses and estimates. Because, oftentimes we don't have data to back up. We don't have an experiment to back up what we believe to say is going to happen. We don't have trials to run. We don't have statistical analysis. But what we can say is using intuition, using educated educated guesses or estimates. That's called subjective probability. So let's take a look here and see. The probability of rolling a double six is 1 in 36. Is that theoretical or classical? Is that empirical, statistical, or is that subjective? The probability of rolling a double six is 1 in 36. What would that be? Theoretical or classical, right? I would call that theoretical. Right? Theoretical and classical is the same thing. Right? Theoretical. Did I run an experiment and say I only got 1 out of 36 trials? No. I'm just saying, based on 36 possible outcomes, 1 of them is a double six. The probability of my car breaking down before the year is over is 2/3. Subjective. Yeah, that would be an example of a subjective. Apparently your car's a clunker. Did I run an experiment on my car and figure out how many times it broke down?
Heck yeah, I have.
Maybe you have, yeah. But if I had run some sort of experiment, that would be statistical probability or empirical probability. You know. And is there any sort of theoretical analysis on? No.
Heck yeah.
The probability of any given person liking the color blue is 0.8.
Factual.
You know, I have in my here, the book says that's empirical or statistical, right? Because it sounds like I have run some sort of experiment, right? We don't have much more backstory on that. However, like in my opinion, like the book says that, but in my opinion, if we're running that study here at Lake, I would say that's more of a subjective thing, right? Because our school colors are red and blue, and people liking blue is more often going to happen, right? So I would say that might be more subjective, but those are kind of toss-ups in there. Theoretical is really easy to point out, right? And if I say I have done some sort of experiment, this implies that I've done some sort of experiment, but I don't necessarily know for sure. All right, let's finish off the notes here. Some other things about probability. The probability of an event E is between 0 and 1 inclusive. You can't have a probability greater than 1. You can't have a probability less than 0. If you have a probability of 0, there is 0 chance of that thing happening. Not necessarily the fact that it's not likely to occur. That is very different. If something is not likely to occur, then it's probably close to 0, but not 0. If the probability of something is 0, then it is definitely not occurring. You're rolling a 7. It's not a possibility. If the probability is 1, then that thing must happen. Don't confuse that with the probability of something tending to happen. If I say I want the probability of me rolling a number, okay, that's 1. So, and again, the closer we get to 0.5, the closer there's an even chance of that thing happening. The closer I get to 1, the more likely that thing is going to happen. Let me bring this over onto the slide here. We also have complements of an event. Come on over, buddy. Come on. There we go. I'll put this all on one slide. The complement of an event. Oh, that can go up a little bit too. Let's just condense this all. There we go. The complement of an event, E, is basically the set of all outcomes in a sample space that are not included in that event. So if I say the probability of a tails, what's the complement of a tails? Heads. If I say rolling a 1, what's the complement of rolling a 1? Rolling a 2, 3, 4, 5, or 6. Right? There's all the other types of outcomes that you could possibly have. Think about complementary angles. I've got a 30-degree angle. The complement of 30 is 60 because it fills up to 90, right? you're thinking about what's the probability of something filling up to 1. Okay, we call that E prime. Not the derivative. Not the derivative. The complement of E is E prime. And then there's a couple ways to write that, a couple ways to think about it. Probability of E plus probability of E prime is 1. The probability of E is equivalent to 1 minus the probability of E prime. And the probability of E prime is 1 minus probability of E. Okay, all those things tie in here. But those are complements. Complements. Watch the spelling there. That is not complement with an I, that is complement with an E. Excuse me. And I'll just write the examples that I've got up here. Get rid of my last slide here, and I'll just write it. If I say there's an event, okay. If I say there is an event where I say rolling and even, that is my event. What's E prime? Right. E prime would be rolling an odd. If I say my event is, and I'm just going to read this off my slide here. Suppose that the probability of the Guardians winning the World Series is 0.2. What is the probability of the Guardians not winning the World Series? 0.8. Pretty simple, right? Complement is just 1 minus that probability. It's, and you got to think about a probability and its complement. There's no other possibilities that could happen. Right? It's got to be all the other items in the sample space. And that's it for the day's lesson. Let me get the homework up here. 7 problems.
Awesome.
Y'all done?
Yeah.
Okay, just go that in back. For the project for chapter 3. So let me just kind of explain what we're going to be doing, because now we basically have all the ins and outs of it. What you're going to be doing in the chapter 3 project, I'm going to give you 2 packets of M&Ms. You're going to count all the colors. And then you're going to find statistical probability, which means, then you're going to find theoretical probability, like, okay, what's the probability that I pull a red at random from my 2 packets of M&Ms? What's the probability that I pull a blue? What's the probability that I pull a red, then a blue? What's the probability that I pull 2 blues together? Which is what we'll continue on to work with in the next 2 sections. Then, once you figure out all those theoretical probabilities, you put them all in a cup, and you shake it up, and then you pull 2. Put it back in. Pull 2, record the colors. Pull 2, record the colors. And you do that like 100 times. And then you're finding statistical probability. And then you figure out your statistical probability of pulling a blue to a red, pulling a red to a red, pulling a red to a blue, and so forth. And in the end, you get to eat it all.
Yeah, that answers my question.
All right, we need to turn off the video. But again, that'll be a week from today. We gotta learn how to find those probabilities first. You're gonna ask the question. Okay. Yep.
That's field.
So look up here.
Yeah.
Right. So what you have here are just raw amounts of scores.
Histogram. So the histogram is one
So
where
what you're gonna do
the
is
plots are
find
touching and add up to
all of your statistics just based off of those. Does that make sense?
it's just like it shouldn't take
Let's say like there was 5.
How many are in?
Okay. So we can do
That
that.
makes
Yeah.
Can you verify that on there? Yeah, that's fine. It's all fancy.
it was fancy. But it was unnecessary. Not that we needed that.
Yeah, I saw it.